I'm Shalini V, working as Assistant Professor of Physics. Today in this video, I'm going to discuss the topic for the session 30 for B.Sc first semester. The topic of this session is Theory of Compound Pendulum and its Properties. So before going to deal with the topic, we have to know what is a simple pendulum, and also we need the formula for moment of a couple or a torque. A simple pendulum is a point mass attached to a light inextensible string and suspended from the fixed support is called as a simple pendulum. And when the simple pendulum is allowed to oscillate, the time period of oscillation of a simple pendulum having a length L is given by T is equal to 2 pi root of L by G. Then what is a moment of a couple or a torque? It is the turning effect of force and is given by the product of force and the perpendicular distance. Then we shall consider compound pendulum. So a compound pendulum is a rigid body which is capable of oscillating freely about the horizontal axis, which passes through a point. So here xy is the horizontal axis about which the rigid body oscillates, and this body is now called as a compound pendulum. Here in this figure, G is the center of gravity of the rigid body. Then let us consider the theory of a compound pendulum. So let this be a compound pendulum which is oscillating about the horizontal axis xy, which passes through the point O. And G is the center of gravity of the body. And when the body is at rest or in equilibrium position, the point G lies exactly below the point O. Let the distance between the point O and G be L. Now, let the body, that is a compound pendulum, be displaced through a very small angle theta. Then a restoring couple within a body acts on it and brings it back to the equilibrium position. But due to inertia of the pendulum starts oscillating about the mean position. Then the moment of a restoring couple or a torque is given by torque tau is equal to force into perpendicular distance. So at the point G dash. So when the body is displaced through a very small angle theta, the new position of G is G dash. G takes the new position G dash, and at this point G dash, the weight is acting vertically downward, that is weight of the body is mg, which is the force here. Then here force is nothing but mg. Perpendicular distance is nothing but, this is the perpendicular distance, which is G dash into A. And G dash into A is nothing but L sine theta. Here L is O, G dash is L, means here this is nothing but an L sine theta. So tau is equal to mg into L sine theta. Since here we have displaced the body through a very small angle, so theta will be very small. So if theta is very small, sine theta is equal to theta. Hence tau is equal to minus mgl theta. Since it is always moving towards the center or equilibrium position, here it is denoted as negative. So therefore the torque acting on the body is equal to minus mgl into theta. Then next, suppose if I is the moment of inertia. So in the previous figure, suppose if I is the moment of inertia of this compound pendulum about an axis xy, then the restoring couple is given by tau is equal to moment of inertia I into angular acceleration alpha, where I is the moment of inertia of this compound pendulum about an axis xy, and alpha is the angular acceleration of the body. Or alpha can be written as equal to d square theta by dt square. So from equations, previous equation 2, and also from this equation, the torque 2 can be written as equal to, that is, since both are the expression for torque, equating the two equations, what you will get is I into d square theta by dt square is equal to minus mgl into theta, or d square theta by dt square is equal to minus mgl divided by I into theta. In this expression, m is a constant for a given rigid body, m is a constant, g is constant, l is fixed, and moment of inertia about the axis, horizontal axis, remains constant. Hence this can be written as equal to, now d square theta by dt square is proportional to minus theta. So that means angular acceleration is proportional to angular displacement and is negative, hence it is towards the mean position. So from this equation, what we can state is angular acceleration of the body is proportional to its displacement, and since it is negative, it is always towards the mean position. So as the angular acceleration is proportional to the angular displacement and is towards the mean position, the oscillations of the compound pendulum are simple harmonic, and if they are simple harmonic, its time period is given by time period t is equal to 2 pi into root of angular displacement by angular acceleration. Then angular displacement is nothing but theta. Angular acceleration from the previous equation, it is mgl by I into theta. Therefore, this is equal to 2 pi into root of I by mgl. Now we have to determine the moment of inertia value I, that is, which is nothing but the moment of inertia of the compound pendulum about an axis passing through xy. Suppose in the same figure, if Ig represent the moment of inertia of the compound pendulum about an axis parallel to the axis xy which passes through the point O. Then the axis xy and also the axis which is considered which passes through the center of gravity, they are two parallel axes. So by using the parallel axis theorem, we can determine the value of I. Therefore, from parallel axis theorem, I is equal to Ig plus m into separation between the two parallel axes is L. So mass into L square. Then, but Ig is nothing but equal to mk square. Therefore, substituting the values, whatever we will get is I is equal to m into k square plus L square. Now, substituting the value of I from equation 6 into the equation 5, the expression for time period is t is equal to 2 pi root of m into k square plus L square divided by mgl. So get cancelled. This is k square plus L square by gl. Or this can be written as k square by L plus L whole divided by g. Now this is the expression for moment, that is the time period of a compound pendulum. If this equation is compared with the time period of a simple pendulum, so the time period of a simple pendulum is given by t is equal to 2 pi root of L by g. So comparing the two equations, so here L is nothing but equal to capital L is equal to k square by L plus L. Now this length is nothing but called as the equivalent length of the simple pendulum. So thus from equation 6, the time period of a compound pendulum is same as that of the simple pendulum, having a length L is equal to k square by L plus L. Hence this length is called as a capital L is called as an equivalent simple pendulum, length of equivalent simple pendulum or reduced length of the simple pendulum. Now the properties of the compound pendulum. So center, what is the first, before that one we have to know what is the center of suspension and center of oscillation. So center of suspension is nothing but the point O through which the horizontal axis passes and about which the pendulum is suspended is called as a center of suspension. Then what is the, if the pendulum is suspended about this point O, and if L1 is the distance of the point O from the center of gravity G, then time period of simple pendulum can be not a simple pendulum. Time period of a compound pendulum about the center of suspension, when suspended about the center of suspension, is given by t is equal to 2 pi root of k square plus L1 square by G into L1. Then what is center of oscillation? So it is a point C on the other side of G, and which is at a distance of L2. So distance from G to C is L2, which is nothing but equal to k square by L1. So these are the definition for center of suspension and center of oscillation. Then knowing this one, interchangeability of center of oscillation and center of suspension. So we can interchange the center of oscillation and center of suspension. That means we have to show that either if we suspend the compound pendulum about the center of oscillation or about the center of suspension, the time period obtained will be same. So for that one, now consider compound pendulum. Let O be the center of suspension and C be the center of oscillation, G be the center of gravity of the compound pendulum. Let L1 be the distance between O to G and L2 be from G to C. Now initially the body is suspended about the point O, that is about center of suspension, that is not a center of suspension. Then time period about the point of suspension is given by T1 equal to 2 pi root of k square plus L1 square by GL1, because the distance between point of suspension to G is L1, hence T1 equal to 2 pi root of k square plus L1 square by GL1. Now reverse the compound pendulum and suspend it about the point C. Then the length becomes L2. So then if we suspend the pendulum about C, then time period of the compound pendulum T2 is equal to 2 pi root of k square plus L2 square by GL2. So you take this as equation number 2. But that we know that the length of the equivalent simple pendulum can be written as L equal to capital L is the length of the equivalent simple pendulum, which is equal to L1 plus k square by L1. But we know that L is equal to, from figure, L is equal to L1 plus L2. Take this as L1 plus L2. Then what you will get is L1 plus L2 is equal to L1 plus k square by L1. Or from this equation, L2 is equal to k square by L1, or k square is equal to L1 into L2. Now take the add on both sides by L2 square. Then you will get k square plus L2 square is equal to L1 plus L2 plus L2 square. Then divide this one by L2. So divide this whole by L2. Then what you will get is L2 plus k square by L2 is equal to L1 plus L2. But we know that L1 plus L2 is nothing but equal to capital L. Therefore, L2 plus k square by L2 is equal to capital L. Now compare the equation 3 and 4. Both are the expression for capital L. Now now equate the on the other side of the equations. Then what you will get is k square by L1 plus L1 is equal to k square by L2 plus L2. Then substituting this one in equation 1 or 2, what you will get is the time period of oscillations about either about the point O or about the point C. They are same. That means T1 is equal to T2. That is, both the point of suspension and point of oscillation can be interchangeable, because the time period of the compound pendulum suspended about either O or about C, they are same. So this is about the interchangeability of center of suspension and center of oscillation. Then what is the conditions for maximum and minimum time periods of a compound pendulum? So at what point we will get a maximum time period, and at what point we will get a minimum time period of a compound pendulum. Then condition for minimum time period is, so T will be minimum when K takes the value is equal to L. That means if the separate, what is this L means? It is the distance between the point of suspension to the center of gravity. If K equal to L means if the separation between the point of suspension of the center of gravity is equal to the radius of gyration of that particular rigid body, at that particular point the time period of the compound pendulum will be minimum. So this is a condition for minimum time period. That is, time period is minimum when the distance between the point of suspension and the center of gravity is equal to the radius of gyration of the pendulum about a parallel axis through the center of gravity. Then condition for the maximum time period. So if L is in a equation for time period of a compound pendulum, we have the L value in the denominator. So if L equal to 0, what you will get is time period will be maximum. So L equal to 0, what this indicates? The axis, that is the horizontal axis, must pass through the center of gravity. So separation between the center of suspension and the center of gravity must be equal to 0. L equal to 0 indicates that separation between the point O and point G is equal to 0. That means we have to suspend a pendulum about the center of gravity. Then at that particular point, we will get a maximum time period. So the time period of a compound pendulum becomes maximum when the axis of suspension passes through the center of gravity of the pendulum. So these are the books which I have referred for this topic. Thank you.